All right, chemistry, this is your video lecture for chapter 9, section 1. We're going to be talking about stoichiometry. Now, section 1 is called Introduction to Stoichiometry, but we're going to move on from that to actually doing stoichiometric calculations in section 2, and then applying those stoichiometric calculations to real-life problems in section 3, things called limiting reagents and percent yield. But let's stick with section 1. So these are the types of questions that you're going to be asked in this section. So consider the following balanced chemical equation. If 2 moles of HCl react, how many moles of H2 are obtained? All right, so this HCl over here in the reactant side, if there are 2 moles of this, how many moles of H2 will be formed? That is a question that you will be asked. How many moles of magnesium will react with 2 moles of HCl? Again, if you have 2 moles of HCl, how much magnesium is required to react with that? If 4 moles of HCl react, how many moles of each product are produced? Each one. Right? If you have 4 moles of HCl, how many moles of magnesium chloride will be obtained? And how many moles of hydrogen gas will be obtained? Lastly, how would you convert from moles of a substance to the masses of a substance? And these are things that we have done in the past. Whether or not we've done a lot of it, that's kind of up in the air, but we have done these things in the past. We're just going to hit them harder in this chapter. All right. Specific things you'll need to do in this section. Define stoichiometry. Define the importance of the mole ratio in stoichiometric calculations, and then write a mole ratio relating to substances in a chemical equation. We'll start with some definitions. There are actually a couple of different kinds of stoichiometry. There's composition stoichiometry, and there's reaction stoichiometry. And the difference between the two really lies in their descriptor. Composition stoichiometry deals with the mass relationships of elements in compounds, within the compound, this single compound. So if you have some large hydrocarbon like glucose, C6H12O6, the mole ratio between carbon and hydrogen is going to be 6 to 12, or if you want to simplify it, 1 to 2. The mole ratio between carbon and oxygen within the glucose is 6 to 6, or 1 to 1 if you simplify it. But it's within the same compound, right? The relationships between the different elements within one compound. Whereas reaction stoichiometry looks a little bit more like what we saw on the last, or 2 slides ago, where we look at an entire chemical equation and we look at relationships between reactants and products, right? Different compounds, but they're within the same reaction.
The amount of a given substance in moles times an appropriate conversion factor is equal to the amount of the unknown substance in moles. The conversion factor is the mole ratio of the unknown substance to the known substance, which can be determined by examining the balanced equation.
All right, there are going to be some different types of problems that you're going to be asked to complete. One type of problem, the given and the unknown quantities, meaning what the problem gives you and what the problem wants you to solve for, are both in moles. They're both amounts of moles. That's one type of stoichiometric problem you'll have to do. And show a little flow chart. We have the amount of the substance given in moles. You're going to convert that into the amount of the unknown substance in moles. Again, you're going from what's known, what the problem gives you, to what the question is asking for. Another problem type, I should say. The given is in moles, but the unknown is in mass. So what we'll do there is we'll go from the moles of whatever is given to the amount of the unknown in moles. And then from the unknown in moles, we'll go to the mass of the unknown in grams. And so in problem type 1, we'll simply be using the mole ratio. That is how we'll do that one conversion, that one step. But when we do a problem type 2, we'll have to use the mole ratio to start out start out with. The 2 mole values there convert from moles of one substance to moles of another. But then we'll have to use the molar mass of that unknown substance. Well, I mean, we'll know what the formula is. We'll be able to calculate that easy enough. But the molar mass of that unknown will be the second conversion factor that we'll use to complete that type of problem. Problem type 3, when the given substance is in mass, but the unknown is in moles. All right, we'll do something very similar to what we just saw, but we'll go the other way. We'll start off with the molar mass of the given substance, converting that into an amount of moles, and then we'll use the mole to mole ratio to finally get that unknown substance in moles. And lastly, problem type number 4, if the given is in mass and the unknown is in mass, we'll start by using the molar mass of the given substance to go from the mass to the moles of the given substance. Use a mole ratio to go from one substance to the other. So now we're talking about the unknown substance. And then we'll use the molar mass of the unknown substance to convert to the mass of the unknown substance. All right, and we need to talk about this magical mole ratio. This is one of the things you'll need to do specifically for this section to identify the significance of the mole ratio. The mole ratio is a conversion factor that relates the amounts in moles of any 2 substances involved in a chemical reaction. For example, we have this particular chemical reaction. We have aluminum oxide decomposing into aluminum and oxygen gas. We have several different mole ratios present. We have the ratio of aluminum oxide to aluminum. It's 2 to 4. We have the mole ratio of aluminum oxide to oxygen. This one's 2 to 3. We also have the ratio between aluminum and oxygen. In this situation, it is 4 to 3. So, same equation, several different mole ratios present. And note, for any of those 3 mole ratios that we have identified there, you can flip them so that the top's on the bottom and the bottom's on the top, depending on what you want to cancel and what you want to move into in terms of your units. And the ratio will stay the same. All right, converting between amounts of moles. All right, so between amounts of moles. First, number 1, identify the amount in moles that you know from the problem. So read the problem. What does it give you? Number 2, using the coefficients of the balanced equation. Remember, we have to be able to balance those equations. Set up the mole ratio with the known substance on bottom and the unknown substance on top. Now realize you want your known substance on the bottom so that unit will cancel out and the unknown unit will be left because it is on top. And lastly, multiply the original amount by that mole ratio. So in terms of stoichiometric calculations, there are actually several different units that can be used and converted in between when it comes to stoichiometry. You can actually convert from the volume of a substance, right? Give you a milliliters of some substance. As long as you have the density, you can use the grams per milliliter unit of the density to get those milliliters to cancel out. Then you'll be in grams. Now you have the mass of a substance. Then you can convert using the molar mass into a number of moles. You can use Avogadro's number to convert into how many units or how many atoms or molecules are present. Or you can use the mole ratio to start talking about a different substance identified as substance B here. Again, you'll be in moles. Then you can convert into, using molar mass into the mass of a substance, and then back into density of a second substance. Or you can use Avogadro's number again to talk about how many units of that substance B are present. So a lot of different movements, a lot of different units can be converted here as long as you understand the basic conversion factors of mole ratio and molar mass.
Four pieces of information are needed to solve a mass-mass problem. The mass of the given substance, the molar mass of the given substance, the mole ratio of the 2 substances, and the molar mass of the unknown substance. For example, how many grams of tin 2 fluoride can be produced by the reaction of tin and 30.00 grams of hydrogen fluoride? First, convert the mass of hydrogen fluoride to moles, using the molar mass calculated from the periodic table. Next, convert the moles of hydrogen fluoride into moles of tin 2 fluoride. Look at the balanced chemical equation to see that the mole ratio of tin 2 fluoride to hydrogen fluoride is 1 to 2. Using the mole ratio, find the number of moles of tin 2 fluoride produced by the reaction. Then convert the moles of tin 2 fluoride into grams using the molar mass calculated from the periodic table. 30.00 grams of hydrogen fluoride can produce 117.5 grams of tin 2 fluoride. Four pieces of information are needed to...
Sorry. Alright, chemistry, that is the end of this video lecture. Make sure you write down any questions you have and make sure you ask them in class. I will see you next period.